So this week is two big topics in respiration. We're going to talk about gas transport, first getting gas into the bloodstream, so diffusion, and transport, mostly by hemoglobin, but not only. And then regulation of ventilation will be the other topic. So that's this week. Let me share with you, and we'll talk about partial pressures. So to talk about gas diffusion and transport, we need to introduce some new terms, and we're going to relate to physics a bit here. We need to define partial pressure. This is the pressure that each gas that's present exerts in the system. So the pressure of the gas is actually what's going to matter. It's related to the gas's concentration, but not completely. We'll get back to that. So we need to know the pressure of oxygen that's in the air, in the alveoli, throughout circulation. So first we need to introduce this basic idea. This is called Dalton's law. Pressure in the atmosphere is the sum of all gases present in the air. So it's going to be an important thing to know here. So I'm going to break down this law for you. Here are three beakers. Let's say in beaker one, we have gas A. Maybe it's oxygen. Here is some gas molecules. The pressure of the system, we're just going to use kind of random units. We're just going to say 10. We can say millimeters of mercury. Sure, let's put our units. In the second beaker here, let's say we have gas B. There is a certain amount of this gas in here. Let's say 5. It's contributing 5 units of pressure. What happens if we add these together? Gas A and B. So I'm going to put 4 of these in here and sum all of the gas A. Let's say we mix these two gases together. So this is gas A plus gas B. What is the total pressure of the system going to be? You should be able to do this from Dalton's law that we have right up there. Pressure in this system is the sum of all gases present. So 10 plus 5 equals 15. And that's Dalton's law. This can be used the other way to break down the proportion of each gas in your system. So what I mean, first here, the presence of one gas does not affect the presence of another one. The total pressure is a sum of all of those gases. And this is going to matter because we want to look at atmospheric. We're going to start with the atmosphere, right? That's what we're breathing in. So let's break down. Let's go the opposite direction. I will erase a little bit of that there so you can see it better. Pressure at sea level of the atmosphere, and you know this from last week, I think it's come up a couple times, is 700 millimeters of mercury. That's also called 1 atmosphere at sea level, 1 ATM. So 760 millimeters of mercury, that is the sum of all gases that are present in our atmosphere at sea level. We want to go from that to what is the proportion that each gas makes up. We can do that by figuring out the percent that each gas contributes. What percent is each gas in our atmosphere? I'm going to give you those. You may have seen this before in a class, probably not your biology class. The percent contribution of each of the main gases in our atmosphere to our atmosphere. Nitrogen is actually the largest proportion. Oxygen at 21%. It's going to be helpful to know that one. Carbon dioxide actually really low, and then other. This is the percent contribution of each gas. We can use these numbers to figure out the partial pressure of each gas in the atmosphere. The partial pressure of this gas, partial pressure, let's say of nitrogen, is going to be equal to the total pressure times the percent or the fraction that it contributes of that gas. Does that make sense? Let's do this, right? So for PN2 of nitrogen, it's going to be 760 PATM at sea level, which was what we're going to start with, right? Is always going to be 760 times 0.79 is 79%. That equals 600 millimeters of mercury. PO2, 760 times 0.21, 160 millimeters of mercury. And lastly, PCO2, 760 times 0.0004 equals 0.3 millimeters of mercury. You don't need to memorize all of these numbers, but you are going to want to know this one because we're going to be looking closely at the partial pressure of oxygen throughout circulation in the alveoli. So this will be a nice reference to have. So why this matters is diffusion is going to occur down these gradients. Partial pressure gradients are kind of like instead of concentration. Diffusion occurs down electrochemical gradients, often concentration, for molecules like glucose, sodium. For gases, we're going to use partial pressure instead. That will become obvious why we do that later on. For now, just know we do. So let's look at this. Let's say you have two air-filled compartments separated by a membrane that allows for diffusion of gases across that membrane. Which way is each of these gases going to move? Hopefully you can figure that out, right? So which way is O2 movement and CO2 movement? They're both going to move down their partial pressure gradients. So that is that way for oxygen and that way for carbon dioxide. Easy peasy. We're going to use this idea when we get to oxygen diffusion, both at the alveoli into the bloodstream, and same idea, bloodstream going to your cells of your body that need oxygen and to get rid of carbon dioxide.